Chapter 7, here we go. You'll notice pumpkins. Yeah, we were supposed to be there at Halloween. We're a little bit behind. But don't worry, this chapter's a lot of review, so I'm going to try to go fast so I don't bore you or waste your time. And I'll go fast as soon as my computer stops stalling. There we go. So, back in the day, there was an argument about light. Is light a bunch of particles that travel through space until they're detected by our eye? Or is light a wave where it travels like a wave of water until it reaches our eye? And there were two arguments. And one was that light was made of particles, and that was argued by Sir Isaac Newton. And he said it has to be particles because light travels in a vacuum, it reflects off of objects, and it exerts a force, so it has to be made up of a particle. And then another one, Huygens, he argued, no way, light has to be made of waves because it reflects like waves, it refracts and diffracts like waves, and it exhibits interference with other objects. And so these two went back and forth, and the question was, which one is it? Well, the answer is both, that light behaves both like a particle and like a wave. Now, bad news. That means we can calculate light characteristics like they're a particle, and we can also calculate light characteristics like it's a wave. Because it's a wave, it has a wavelength, which remember is represented by the symbol lambda, kind of looks like an upside down Y, and that is the distance from crest to crest or trough to trough. So it's the distance from a peak to a peak or a valley to a valley on a wave. Your amplitude is half the distance, vertical distance, so we usually measure it from the origin, which is in the middle of the wave, to the top. Then you have frequency. Now that V-looking thing is actually a nu, N-U, and that's a Greek letter. When we write it, you're going to see me write it a little more curly than that to distinguish it from V, which would be velocity. And frequency tells you how many waves you see pass a point in a given second. So if you were to time yourself for 1 second, how many waves do you see pass yourself? So this is just a picture to kind of depict these things to you. Wavelength is crest to crest, or these are crest to crest, or it could be measured trough to trough. The amplitude is half of the vertical distance, and the origin is the line that runs through the middle. And then crests are at the top and troughs are at the bottom. Now, if you compare these three waves, the red, the green, and the blue, you have to be able to analyze them for frequency, wavelength, and energy. So just looking at them, which one do you think has more energy? And it's kind of your intuition, but if you said blue, you'd be right. The blue has more energy, but which one has the larger wavelength? In other words, which one has the larger distance between the two peaks? And yes, it would be red because there's more space between the peaks. But which one do you see more often or more frequently? And if you look at this picture, this is 1 second. So you look and you say, okay, how many waves do you see in a second? So the first one, you see, 4 waves. But the second one, you see 8. And then the third one, you see 16. So there's more waves in the blue, so it has a higher frequency. You are going to be responsible to know the relationship between these. The longer the wavelength, the lower frequency. So the bigger the distance, the less waves I see, and the lower energy that I have. Notice, when wavelength is high, frequency and energy are low. So wavelength is inversely related to frequency and energy. But frequency and energy are directly related to one another, because when one's low, the other's low. And this is just showing you the same type of relationship, but with the blue wave. So essentially what I just said is true. Wavelength and frequency are inversely related. Wavelength and energy are inversely related, but frequency and energy are directly related. So if the frequency goes up, the energy goes up. There are 7 regions of the electromagnetic spectrum you are responsible to know. In case you're interested, we can play this song in class, but it starts with radio waves, then microwaves, then infrared, then visible light, ultraviolet, X-ray, gamma ray. Yes, you'll be asked questions on the spectrum this year. You must know that the radio side has long wavelength, low frequency, and low energy, and the gamma side has high frequency, high energy, and short wavelength. So that's just showing you here what I just said. You need to know the different sides. Also, with invisible light in the middle, you need to know that visible light is made up of Roy G. Biv, because I can ask you questions like, is yellow light or violet light more energetic? And clearly, because violet is closer to the gamma ray side, it would be higher energy. Now, like I said, there are calculations that can be done with the light. And so the first one is C equals lambda nu. And this equation is capitalizing on the fact that wavelength and frequency are directly related by the speed of light. So, by the way, I said directly, I meant inversely, I'm apologizing. C, the variable C, is the speed of light, and light moves at 2.998 times 10 to the 8 meters every second. So light's booking it. Your wavelength is your lambda, and just so you know, it has to be in meters. And the reason it has to be in meters is your speed of light is in meters. If you need to convert, oftentimes wavelengths are provided in nanometers. Of course, they can be provided in anything, centimeters, millimeters, whatever, but they're often in nanometers. So you'll need to remember that a meter is equal to 1 times 10 to the 9th nanometers, because you will have to convert before you plug it in. And then nu is frequency, and frequency has 3 units, all acceptable units. One of them is the hertz, which is an Hz, and the H needs to be capitalized. And the hertz is the same as 1 over seconds, which is the same thing as saying s to the minus 1, because that means to do the inverse of seconds, which would be 1 over s. So here is your first sample problem. Calculate the frequency in s to the minus 1 of an X-ray that has a wavelength of 8.21 nanometers. And when you are doing any sort of calculation, you are going to want to put down the equation that you're choosing to use before you move on to the rest of the problem. This is good practice for AP because the graders will be more apt to give you points if they can follow your work. So you really need to write the equation down. So what you're going to notice is when you read a question, and it's not in your notes, already in a nice organized section, you need to realize that frequency has been mentioned, and frequency is nu. Wavelength has been mentioned, which is lambda. And the only equation that relates the two of them is C equals lambda nu. Now you're going to plug in what you know in order to solve for what you don't know. Now remember, C is a constant. It is always 2.998 times 10 to the 8th meters per second. You were provided wavelength. Wavelength is in nanometers. But remember what I said, because the speed is in meters, you have to put this into meters. So 1 meter is 1 times 10 to the 9th nanometer. You're going to get 8.21 times 10 to the negative 9th nanometers. I'm sorry, meters. You are going to fill that into your work. And you're going to solve for what you don't know, which is frequency. So you get out your calculator, which I'm doing as well. And you divide it. And sig figs. So let's talk sig figs. C, the speed of light, is a constant. So it's always going to be this number. Therefore, it does not count for sig figs. The other number we had, the 8.21, has 3 sig figs. So I'm going to put the answer with 3 sig figs. And I get... Oh, that's not right. Hold on. 2.998 e to the 8th divided by 8.21 e to the negative 9. I get 3.65 times 10 to the 16th hertz. Now you can write hertz, you can write 1 over s, you can write s to the minus 1, whatever you want to do, but they're all equivalent units. So here's another example. A submarine radioed information back to a command ship above. The electromagnetic signals had to travel about 6.4 times 10 to the 5th meters. how long did it take for those signals to reach the ship? Now you'll notice this one's not as cut and dry. It doesn't mention frequency. It doesn't mention wavelengths. So we got to kind of think on our feet. If the signals have to travel that many meters, it's a length. And the length that we deal with is wavelength. So this must be my wavelength. And when they ask how long, they're asking time. But remember, time is related to frequency because frequency has units of 1/seconds. So if I can find the frequency, I can then relate it to time. So the first thing we're going to do is we're going to solve for frequency. Since I have wavelength, I'll use C equals lambda nu. My wavelength is 6.4 times 10 to the 5th. And my frequency I'm solving. You always know C. You plug it into your calculator. Okay, so I quick lost reception there, so I'm just going to catch back up. We're going to use the equation that relates wavelength and frequency. We know that the C is always 2.998 times 10 to the 8th meters per second. They also gave you the length in meters, so you don't have to change it in any way. And we're going to solve for frequency. And you may be thinking, why are we solving for frequency when we want time? And I will show you in just a minute. So with 2 sig figs, because that has 2 sig figs, you get 470 hertz. Now, remember, a hertz is a 1/second. So right now, I want the opposite of this. So right now, I have 1/seconds, and I want seconds. So if I inverse this, I will get seconds. And inverse means do 1/. So if I do 1/470 1/seconds, I'll end up with the answer in seconds. So you need to realize time and frequency are inversely related. And I get 0.0021 seconds, which is crazy because what that means is for a submarine to send a signal, 640,000 meters, it takes less than 1 second. That's how fast electromagnetic radiation travels. So electromagnetic radiation can do one of 3 things. It can transmit, which means it'll go through matter without even interacting with it. It'll just pass right through it. It can be absorbed by an atom, an ion, or a molecule, and when that atom, ion, or molecule absorbs that radiation, it'll take it to a higher energy state. Or radiation can be emitted by an atom, ion, or molecule as light, which will allow it to go back to a lower energy state. And if you did flame tests your honors chem year, then you experienced this because you got to see when it would absorb or release light. Well, you got to see it release energy in the form of light after it had absorbed it. So this is just a picture to show you the 2 options really of absorption and emission. So if the green here would be the radiation, if the yellow electron receives radiation in the top picture, it'll be promoted to a higher level, which is where you see the red. And in the bottom picture, if it loses a radiation, which is the green coming off, if the red one loses radiation, it'll drop to a lower level. All right, so now, even though we've talked about it as a wave, remember that light is also a particle. And there's something called the photoelectric effect. It was first observed by Hertz, and then later Einstein explained it. And essentially this effect shows that when light falls on group 1A metals, so lithium, sodium, potassium, etc., electrons will be emitted. So when light hits them, they let off electrons. The brighter the light, the more electrons will be let off. And the energy of the electrons that come off depends on the frequency of light you hit it with. And I'm going to demonstrate that for you in a picture. So essentially in this picture you see that there is an incoming light that is red here. and it's going to hit the surface of the metal, which is blue. And when it does that, the light is a form of energy, and it causes the electrons to come off the surface of the metal. Now, that is the photoelectric effect. Now, remember, though, that electrons are not going to just come off of the surface of the metal without any amount of energy input. So there's a certain amount of energy that's needed to remove an electron from the metal surface. So when that radiation comes in to remove the electron, some of that radiation originally will be used to take it off the surface. If there's not enough energy coming in, then the electron won't come off. It'll just stay there. If there is enough for it to come off, the electron will come off the metal surface, but just remember this. This is your total energy that you put in. This is your E, your total energy. There's a certain amount of energy it takes to take this electron off, which is right here, and that would be the amount of energy it takes to remove it. We call that ionization energy. And this would be the kinetic energy of the electron after it's off. So, what I'm saying is, if this up here, if your original energy is 60 kilojoules, and it takes you 10 kilojoules to take it off, what that means is you still have 50 kilojoules to provide kinetic energy to the electron, because the ionization energy and the kinetic energy have to total to the original energy. Now, this is important to remember because electrons that are close to the nucleus are harder to remove. So instead of it taking, when that irradiation comes in, instead of it taking 10 kilojoules, it may take this one 30 kilojoules. Now, the problem with that is this. If it takes 30 kilojoules to remove it and I only had 60, then the electron will only get a kinetic energy equivalent to 30 kilojoules, which means it'll be moving slower with less kinetic energy than the electron would that was further away from the nucleus. So the key is core electrons, which are bound to the nucleus, come off with less kinetic energy than valence electrons, because valence electrons are in the outer shells and they don't require as much energy to come off. So studies of this entire effect led to another equation that you're familiar with. You've probably seen it last year. You probably saw it as E equals H nu. So E equals H nu. H right here is Planck's constant, which we're going to use 6.626 times 10 to the negative 34th. That negative is hard to see. And one thing that I'm going to caution you on is that the energy units here come out in joules per photon, and that's something that we never emphasized last year, but we're going to focus on this year. And then remember that nu is still frequency, and remember frequency is hertz or 1/seconds for units. Alright, so Max Planck is the one that talked about light as a particle. He's the one who revisited it, and he proposed that light is made up of particles that each carry a certain amount of energy, and that the amount of energy is also related to the frequency and the wavelength. And so he took that law that I just showed you, the E equals H nu, and he also created E equals Hc over lambda. So this one relates wavelength and energy, whereas this one relates energy and frequency. And again, this is the value of H that we're going to use. So calculate the energy in joules of a photon of violet light that has a frequency of 6.15 times 10 to the 14th. So the first thing we're going to do is pick out keywords. We have energy and we have frequency. So we need to find the equation that has energy and frequency, which happens to be E equals H nu. We are trying to solve for energy. H is 6.626 times 10 to the negative 34th joules times seconds. And our frequency needs to be in hertz or s to the minus 1, which it is, and we just plug it in. 6.15 times 10 to the 14th s to the minus 1. Now, remember, and I mentioned it just briefly before, when you get your answer, it's not just joules. The answer, which is 4.07 times 10 to the negative 19th, is joules per photon. Now, two things. One, H is a constant, so I didn't look at it for sig figs. Since this had 3, I put 3 in my answer. Two, this question asks for joules of a or 1 photon. If it asks for 10 photons, you'd have to times this number by 10 because the answer you get will by default be for 1 photon. So what if you needed to determine the energy in kilojoules per mole of a photon of blue-green light with a wavelength of 486 nanometers? Well, number 1, you're trying to find energy. You have wavelength. So the equation we used previously on the last problem won't work. We have to use something that relates energy and wavelength, which will be E equals hc over lambda. Now, you know H. You know C. They're constants. You plug them in. Wavelength has to be in meters. This is in nanometers. So they converted it to meters and they plugged it in. Now, when you solve this, this is the answer you get, but remember, energy is in joules per photon. And this question specifically says kilojoules per mole. So you're not done. So to finish it up, you have to take your answer, which I think it's probably easier to show you here. You're going to take your answer and you're going to write it like this. 4.09 times 10 to the negative 19th joules per 1 photon. Okay, now the first part's easy, joules to kilojoules. There are 1,000 joules in a kilojoule. And then last, you have to get from photons to moles. And think about it, a photon is a small particle of light. That's what a photon is. So it's just like the atom. So to go, how many are in a mole is Avogadro's number. Yep, that's right. I said it, Avogadro's number. So you would take 4.09 times 10 to the negative 19th. You're going to divide it by 1,000. And you're going to times it by 6.02, EE23. And you get 2.46 times 10 to the 40th. It can't be 40th. Nope, I didn't do a negative. See, even I knew I did something wrong. You are going to get 200 and... Okay, so you get 246, and then your units would be kilojoules per mole. So the lesson is, whenever you're reading a problem, make sure you pay attention to the units they want. Joules per photon, no problem. The answer will come out that way. If it asks for kilojoules per mole or anything to do with joules per mole, you're going to need to do some conversions. So here's an example in your notes. A laser produces a red light of wavelength, lambda, 632.8 nanometers. No good, because it's in nanometers. Calculate the energy in kilojoules of 1 mole of photons of this red light. So first I need an equation that involves E and lambda, which is E equals hc over lambda. H is 6.626 times 10 to the negative 34th joules per second. I'm not going to put units because I truly don't have room on this slide, but you should. 2.998 times 10 to the 8th meters per second for C. And remember, on the bottom, you have to put your wavelength, but you need to convert it to meters first. And remember, there are 1 times 10 to the 9th nanometers in a meter. Now, when you take 632.8 and you divide it by 1 times 10 to the 9th, you get 6.328 times 10 to the negative 7th meters. And I'm sorry, it's very tight. 6.328 times 10 to the negative 7th meters. Now plug all of that into your calculator and do sig figs, keeping in mind that both H and C are constants that will not be considered for sig figs. That leaves solely the wavelength, which has 4 sig figs, so you're going to want 4 sig figs in your answer. And the answer that I got was 3.139 times 10 to the negative 19th. So 3.139 times 10 to the negative 19th joules per photon. And the problem is this question specifically says kilojoules per mole. So I'm going to go from the joule to the kilojoule. And then, since I'm out of room up there, we'll wrap around the next line here, and I will do that there are, and remember, photons were on the bottom, so photons need to go on the top here, mole on the bottom. There are 6.02 times 10 to the 23rd photons in a mole. I'm going to take 3.139 e to the negative 19, divide by 1,000, times by 6.02 times 10 to the 23rd, and I get 1.890 times 10 to the second kilojoules per mole. All set. All right, so a little more history review. J.J. Thomson was the one who discovered the electron in his cathode ray tube experiment. What he noticed was that if he used a cathode ray, there was a beam of light that would normally hit at B, point B on that yellow disk. However, if he put a magnetic field around the actual beam, he noticed that it started to bend. So if he put the negative electrode, he noticed that the beam would bend away from it, so it would become like C. If he put the positive electrode, it would come towards it. So like this red one, the C would come towards it, and he deduced that the ray must be made of negative particles, which he called the electron. So this is a better picture of it because that other one can be confusing. If you notice, the electrons are going towards the positive plate because they are attracted to it, since they are negative and the plate is positive. Thomson further created the atomic model to kind of demonstrate what he had found. Instead of just an indivisible atom with no protons, neutrons, or electrons, he now knew about protons in theory, so he made the whole dough or blue sphere positive, and then he put negatively charged electrons in it. They call it the plum pudding model because he was British and it reminded him of plum pudding. A lot of students remember it as the chocolate chip cookie model because it kind of looks like one. Notice he was missing some things like a nucleus and neutrons though. In 1909, Robert Millikan actually was able to figure out the charge of an electron, and he basically suspended it in an apparatus between two magnetic plates to figure out its mass to charge ratio. You don't have to know anything about how Millikan did it. One of the most important people is Rutherford. Rutherford was the one that discovered the nucleus by playing with radioactive alpha particles. He used the alpha particles and threw them at a piece of gold foil. As he shot them towards a piece of gold foil, he noticed that most of them went through the foil no problem. And remember, this foil is like a piece of tissue paper. It's very tiny. However, every once in a while, one of them would kind of bounce off to the side, which he thought was weird. But he shot 8,000 particles, and what really got him was the one that came back at him. And the one that came back at him proved to him that it had hit something hard. But what could it possibly hit that was hard in a piece of tissue like metal? And what he deduced was there has to be something very small, because 7,999 particles didn't hit it dead on. So it had to be small, but it also had to be dense to cause it to come back. And so he changed Thomson's model to include the nucleus. And in the nucleus, he put the neutrons. His discovery, he quoted it as, it was as if you fired a 15-inch shell, which is a piece of heavy artillery to be used in war, at a sheet of tissue paper, and it came back to hit you. Like, it was impossible what he had just discovered, but he knew he was onto something. So just remember that the nucleus is extremely small, and if you wanted to use the following analogy, if an atom is as big as a football stadium, the nucleus would be the size of an ant on the 50-yard line. It's extremely tiny. There's a lot of empty space in the atom because the nucleus is so small. Now, in 1932, James Chadwick was the one who discovered the last subatomic particle. It was the neutron, which is why I put Mr. Jimmy Neutron here, and that should also help you remember James Jimmy Neutron created or found the neutron, James Chadwick. Now, Bohr. Niels Bohr, we didn't really talk so much about last year, but you're going to do more this year. Bohr worked a lot with the hydrogen atom. And what Bohr realized was that electrons that are close to the nucleus are lower in energy and more stable because they're more attracted to the nucleus. So electrostatic attraction is fancy words for positive and negative attract. Now, he used the letter N to designate the energy level that the electrons were in. The lower N, the closer it is to the nucleus. Quantum numbers. just saying. Now, key to Bohr's model was he believed if they were in a particular level, if they're in a particular N, they have to have energy to move to another N or lose energy to drop down to another N. They cannot just freely move between these energy levels. They are restricted. So they like to liken his model to planets orbiting the sun, that they're stuck in their path unless something alters that path. So like I said, it's like the planet model. Every level represents a new layer, and at the center is the nucleus. Oh my God. Sorry, my dog's crazy. Okay, so Bohr actually studied spectra that would produce if you excited atoms in a gas discharge tube. So last year, if you were in my class, you got to see these in those spectroscopes when we looked at light with those crazy little viewer glasses. And what happens is you can actually see the lines that are produced by the electrons in the atom when you look at them. Well, Bohr actually studied these. And what he figured out was that where are each one of these lines coming from? And like I said, he really studied the hydrogen atom because it's the simplest atom we have because it only has one electron to promote or release energy. And so if you'll notice, the top spectrum is the hydrogen, and he was like, I'm going to figure out why I see these 4 lines. So he looked at all the possible transitions the hydrogen's 1 electron could make. Now, it could start in energy level 1 and move up 1 energy level, move up 2 energy levels, move up 3. And essentially, he plotted all these different options that the hydrogen electron could move. And he found that the electron in hydrogen occupies discrete energy levels. So it has to be in a level, it cannot be between them. Much like the rungs on a ladder, that if you're on a rung of a ladder, you cannot be between rungs. You have to be on one rung or on the next. You cannot be between. The atom will not radiate energy if the electron is in an energy level, but if the electron falls to a lower energy level, then radiation will be released that's equal to the amount of energy that's different between the 2 energy levels. So this picture is exactly what Bohr figured out. That the electron, which starts in energy level 1, which is step 1 all the way at the bottom, has to take a fairly large leap to get to energy level 2. But then, to go from 2 to 3, it takes a little less energy to make that jump. 3 to 4 is even less, 4 to 5 is even less. So essentially, the inner levels of the atom require, if the electron is in those, it requires more energy to move it out of that level and up than it does in subsequent levels. His model was great because he was able to account for the lines you saw in hydrogen, and he was also able to calculate the radius of hydrogen. However, his model doesn't work for anything but hydrogen, and it does not explain why energy is quantized. So eventually they had to scrap Bohr's model, which led us to the quantum mechanical model we have today. However, that doesn't mean we threw out Bohr's model. We still use it to figure out some information for a hydrogen atom only. That's a huge hint. You can't use Bohr for anything but a hydrogen atom. So if the problem is mentioning hydrogen, you kind of have an idea of what you need to do. So this was his equation that said, you know what? If you want to know how much energy there is in a given energy level for an electron, you use the following equation. Negative B, which is Bohr's constant, another number you get to memorize, like H or C, over N squared. And N is the energy level. So energy level 1 is the one closest to the nucleus, then 2 would be a little further, and so on and so forth. Now, B, The value of B that you must know is 2.179 times 10 to the negative 18th, and the units of that are joules. Now, Bohr didn't just figure out how much energy you have in a particular level, he also figured out how much energy it would take to move between levels. And to do that, you do the following equation. The energy that is between levels is equal to Bohr's constant times 1 over the initial energy level squared minus 1 over the final energy level squared. So calculate the energy change in joules that occurs when an electron falls from the 5th energy level to the 3rd. All you have to do is use this equation. Bohr's constant is 2.179 times 10 to the negative 18th joules. 1 over, now remember, the initial energy level goes first, and the initial energy level was the 5th, but you have to square 5. So 1 over 5 squared is 25. And then the final energy level is the 3rd, and 1 over 3 squared is 9. Well, not 1 over. 3 squared is 9, is what I'm trying to say. Now, in your calculator, I suggest, probably for most of you, that you start here on your calculator, that you do 1 divided by 25 minus 1 divided by 9. Then times whatever you get by 2.179 times 10 to the negative 18th. And you'll notice I got a negative 1.5 times 10 to the negative 19th joules. And to me, that makes sense because the electron went from the 5th energy level down to the 3rd. So I expect a negative answer. And why? Because to move down energy levels, it's going to need to release energy. So the negative makes sense. Now, sig figs here, there's nothing to go off of. So just round your answer to probably 2 or 3 sig figs and call it a day. These are typically multiple choice questions, not written, so you don't have to panic about sig figs. So here's an example. Calculate the frequency, that's new, of the radiation released by the transition of an electron in a hydrogen atom from the energy level n equals 4 to n equals 1. Well, you only have one equation that involves 2 energy levels for Bohr, and it's the one we just used. Here's the problem. This equation, while it's going to help us out, is not going to give us ultimately what we need. This is going to give us energy. The question asks for frequency. So you're going to have to use not 1, but 2 equations in this question. So 1 over 4 squared is 1 over 16, and 1 over 1 squared is going to be 1. So I'm going to first plug it in to get my energy, which I get a negative 2.04 times 10 to the negative 18th joules. Now, that tells me energy is released. And I expected energy to be released. It made sense. It dropped energy levels. However, when you go to calculate frequency, you need the equation that relates energy and frequency, which is this one. But when you go to plug in your energy, you cannot leave it negative because what you will get is a negative frequency, which means you saw a negative number of waves in a given second. That can't happen. So you need to take the absolute value of what you got because it's theoretically impossible to have negative frequency and use that to solve for the wavelength. Not a room. So that energy I got is equal to 6.626 times 10 to the negative 34th times nu. So all I'm going to do is divide 2.04 times 10 to the negative 18th divided by 6.626 times 10 to the negative 34th. And I get 3.08 times 10 to the 15th, and then frequency is hertz. So 3.08 times 10 to the 15th hertz is the answer. And I will stop there.